Hi, welcome to our project. My name is Tieming, and here are my two teammates, Wenhao, Cui, and Guangrui, Shen. And we want to introduce a surrounding motion predict module for autonomous vehicle. So our task in one slide is that we want to predict the surrounding agent motion of the autonomous vehicle over 5 seconds, given the historical 1 second positions. And that would be very useful for planning self-driving vehicles movement. So we have tried a lot of stuff, but we finally find deep learning techniques like CNNs and how to ensemble them into 3 trajectories will be very helpful. And here are our outline. For project overview, we use L5Kit, that Python library, to assess and visualize the data set. And we built motion prediction module using ResNet 34, and we shift into Mixnet, and finally we assemble these modules. Then we choose negative multi-log likelihood as the evaluate metric. So we got a lot of challenges. One challenge is that we want to choose our best architecture that has a very good inference module speed. In order to compromise the module speed and the prediction capabilities, we transit into Mixnet as our architecture. And so the next challenge is to how to understand Mixnet. And we want to decide which loss function to use on different training stages. Fourthly, the ensemble models will apply into multiple trajectories because the real world road environment is full of ambiguity. And finally, we want to understand the influence of the parameters provided by the data set, which contains raster size and pixel size and the batch size, and also traffic light mask. And as you can see from this data set, it consists of over 170 scenes, so the scenes is really big. And the next.
So our baseline model we use is ResNet 34. We tried the pre-trained ResNet 34 and set the number of input channels, which is 25. It means that we need 10 historical frame and 1 current frame, and each frame contains ego and agents that are on different channels. So we multiply 2 here, and the 3 means the RGB channels that are for the semantic map. And the output size is the 100 because we output 50 frames into coordinates. And next, another architecture we use is Mixnet. The intuition is that the smaller kernels could capture lower resolution details and the larger could capture relative higher resolution details. So if we blend multiple kernel sizes into a single layer, we could construct a single mixed convolutional layer. So the Mixnet is ultimately using a range of 1 to 5 kernels, which we consider to be the best standard. And next slide. Each of our 3 members tried 3 different Mixnet models, medium, large, and X-large. And as the same before, we set the input channels 25 and output size 100. And next slide. Actually, we use several metrics and finally choose smooth L1 loss as one of our training loss function. Because as we can see that in this picture, it is when the difference between the predictions and the ground truth is relatively small, it could become L2 loss. And when the difference is relatively larger, it could become L1 loss. So it's often used in regression problem or in the equation that exists relative big numbers in features. The next slide. Another metric that we use is negative multi-log likelihood. The idea is that consider that the ground truth positions of a sample trajectory like x1, y1, x2, y2, and so forth. And we have 3 predicted positions now represented by means, and then set 3 confidences, say, of the 3 hypotheses. The assumption is that we assume the ground truth positions are all independent Gaussian mixture model. So we could get the likelihood given the confidences and the predictions. So we just by using the log operation and negative the probability distribution, we could get the NLL formulation, which is shown in the lower right. Next.
Okay, in implementation, first we need to visualize our result using L5 kit library from Lake. Especially we use rasterization and visualization. Rasterization can show all vehicles on the frame, like this blue agent car and green eagle car. And visualization can draw trajectory on image, like this pink trajectory. Next. When we rasterize all vehicles on each frame in a scene, we can make a GIF to see all cars' movements. Next. We need to set configurations for training and validate dataset. All these below parameters are needed to build the rasterized frame. Some parameters are very important to train a good model, like raster size, batch size, and traffic light. Next. Like we can remove the traffic light mask layer due to the fact that the history of traffic signal may have a counterproductive effect for the model. For example, the traffic light was red in past 1 second. If we set the traffic light mask layer, the model would predict the car in the same position in the next 5 seconds. However, in fact, the actual result, the car, it may move a little bit, so it may have counterproductive effects. About the raster size, it's the image size of pixels. We can see the bottom pictures. If we choose a bigger pixels, we can have more surrounding areas. So we can have more agents. So how do we decide the raster size? We believe it's related to the speed. For me, I try to draw entire trajectory on each frame. So I need to ensure after 5 seconds, the eagle car is still on the same frame. So I test it. The max distance is 200 pixels and the eagle car is in the middle left of the picture. Finally, I set the raster size with 300 pixels. About the batch size, we first set batch size 12, but we got a bad performance. It couldn't recognize the curve lines in the frame. We are pretty sure that it's because that some small batch size, sometimes it won't have curve lines situation at all, which cannot improve the model from the loss function. After we set the batch size 32, it performs very well. After we trained several models, the best model is Mixnet XL, and the batch size is 32. And we trained 43,500 iterations. The learning rate is 10-4 with LR regularizer with YDK rate 10-6. And we use Atom optimizer. The loss function, firstly, we use a smooth L1 to make it converge easier, and then we use negative log likelihood to get a better performance. Next. In this box, you can see our best single trajectory model is Mixnet XL, and the validation score is 51.8. And then we ensemble 3 trajectory with k-means. We get a better performance. The validation score is 31.4. Next. After that, we visualize the result. You can see the picture. The pink trajectory is the ground truth trajectory, and the blue trajectory is the predict trajectory. You can see this picture. The prediction is very good in straight lines. Next. The performance is also very good in curve lines. Next. Also very good in stop signs. Next.
Okay, so besides the CNN module, we have tried a lot of tricks. So one trick we tried is to penalize more on some corner cases. So as the corner cases means some cars may pull over or turn or make a U-turn. So if the deviation angle is approximately, it's getting larger, we want to penalize these circumstances more. And the other algorithm we use is k-means. We want to ensemble more like 10 models into 3. So the k-means based on the Euclidean space, it will cluster several modules and vote 3 cluster centroids to represent them. And it is very useful when the checkpoints are set. If we are not sure whether modules are underfitting and overfitting, and k-means outperforms the confidence ensemble by 3.5. And the conclusion is that we want to train more samples, and we should be very patient when fine-tuning the hyperparameters. And it works to try different metrics as the loss function. And future, by future work, we want to try GAN and LSTM encoder decoder, as we read from the paper. That's all.